121 students, I have a little more time to put some information in front of you that helps us grasp what's going on in Chapter 2. Skip the update showing here. And recognize that we need to be thinking about where we're going with the learning objectives. So we'll start here on this view of the list of learning objectives. We're thinking about quantum numbers and what that has to do with orbitals. And we began a little bit of this conversation in class, but here is a time for you to hear about some things that are in the book that we might not spend as much time on in class. All right, so the quantum mechanical model of the atom is derived from the earlier parts of the 20th century by physicists who did some calculations based on all these various experiments that went into understanding protons, neutrons, electrons, the nucleus, and the energies they have, and their wave and particle properties. And Schrödinger's hypothesis, his models suggest that the electron has wave-like properties that can be help to predict where the electrons will be found. Werner Heisenberg, in a very similar time frame, determined that we can't exactly know where electrons are because the simple act of trying to measure them or determine where they are changes their location and influences their location. So Heisenberg's uncertainty principle derives from that. The orbitals that we understand come from this quantum mechanical model. It has to do with the fact that there are only certain places where the electrons will occur. They can't be halfway in between. There will only be certain quantum number designations or places described by quantum numbers explaining where these electrons are likely to be. The wave equation that Schrödinger came up with was solved using these different quantum numbers, and there's 4 of them. We're going to start with 3 for the moment. And the quantum numbers put into this equation come up with what we have called the Greek letter psi, describes an orbital. And the probability of finding an electron in a certain region of space becomes psi squared. So psi is 1 piece and psi squared. We'll hear about both of those in some cases, but they're functions derived from quantum numbers that are 3 parameters that go into that calculation. Their letters are n, l, and m. They're m sub l, and we'll have to describe each of them gradually. So the principal quantum number is n. The first number in the series when you list the quantum numbers is going to be n. It is always a positive integer. It's going to be as small as 1, and it can go up to various other numbers. We won't see many examples that go beyond 4 and 5. That's possible, but not so often. It tells us about the size and the energy level of that orbital. The orbital is where the electron is going to be found, and n is typically going to be describing what we call a shell. The shell of where the electrons occur is described by the letter n, 1, 2, 3, or 4, or whatever. And as the value of n increases, the energy of the electron in whatever orbital it is going to become larger, and so does its distance from the nucleus. So the distance of the nucleus from the nucleus correlates to how much energy the electron has. So as higher values of n have higher energies, and lower values of n have lower energies. Higher values of n are closer to farther from the nucleus. Lower values of n are the opposite. So let's take a look at a diagram. So if you think about concentric spheres and the nucleus being the center of it, the Schrödinger wave equation using those quantum numbers comes up with a way to predict these orbitals. So the psi is that Greek letter that describes the orbital, a function of 4 quantum numbers, but let's focus on n for a moment. So n, if n is the principal quantum number, and that gives us the shell number, then it also correlates to the distance of the electrons from the nucleus. The first shell for n equals 1 is going to be the smallest. It's closest to the nucleus. The second shell, n equals 2, will be the second shell, larger than the first shell, and the nucleus, of course, is in the center. And then when n equals 3, you have the third shell. Each of these shells is successively larger, and the electrons are going to become farther from the nucleus. The next quantum number is called the angular momentum quantum number L. These letters are typically italicized, but that's not a big emphasis. You'll notice that as you go along, perhaps. The angular momentum quantum number is going to describe the shape of an orbital or its subshell. So there's going to be shells, then subshells. We'll gradually connect the quantum numbers and the shells and subshells as we work through this. And so the quantum number, the second of the set, is going to describe those subshells. There are going to be n different shapes for orbitals. And if n is 1, then there are going to be only the one shape where L equals 0. And with n is 2, there's going to be 1 and 0. So L can be 2 possibilities when n equals 2. So there's the same number of shapes as there are numbers of shells. And then when n equals 3, the third quantum number can have values of 0, 1, and 2. So there's 3 values when you're in the third shell. There are 2 values for L when you're in the second shell. And there's only 1 value for L, the magnetic angular momentum quantum number, sorry if I said that wrong, in the first shell. When you have L equals 0, here's the values that we can come up with here. Describe different subshells, as I was beginning to allude here. And so when L equals 0, we call that subshell the S subshell. And always and only when L equals 0, that is the one subshell that is indicated. When L equals 1, that's the next possibility, and it only occurs when you get to the second shell. Then you come to the P subshell, and then when you have L equals 2, doesn't occur until you get to the third shell. Then you're going to have the D subshell. Notice they all have names: sharp, principal, and diffuse. These are derived from spectral information. Remember how atomic line spectra were observed for various elements that began to give clues to the electronic nature of elements. And so sharp, principal, and diffuse lines were observed in these spectra. You do not have to make sense of which one gets its name why, but you can imagine where a line might be sharp or diffuse. When you get to the last of these choices here, L equals 3, the subshell is described as the F subshell, and that has a different characteristic from the other 3. So calling it fundamental means nothing to us at this point. It's just an interpretation of the letters that are associated with each of these shells. Subshells. All right, now continuing. So we have this psi, Greek letter psi, is a function of a set of 3 quantum numbers plus 1 more. And that we've described n and L so far. What about m sub L? Well, that one is the m as a magnetic quantum number. And L was angular and n was a principal one. So m sub L is, again, an italicized letter typically, but it's not always obvious in our representations. And it has what possibilities? For a given value of L, there will be 2L plus 1 values of the m sub L, the magnetic quantum number. How does that work? So if you have m sub L being 0, 1, and plus 1, that's because you have 1 for your value of L. So that would give you 2L plus 1 when L equals 1. M sub L can have 3 values, and they're going to be the opposite of L and 0 and 1. So this is L, not 1. I read that wrong when I looked at it first. So it'll go from negative L to positive L with the integer values in between. Integers will be used here. So if L equals 1, we'll see what that comes into. So start off with L equals 1. We call that a p orbital. That was on the previous slide. And the 3 values you can get are going to be -1, 0, and 1. For L equals 1, those are the only possibilities for m sub L, the magnetic quantum number. 3 different possibilities, but that means within the p orbital, 3 different values of this magnetic quantum number may apply to electrons in that spot. We're going to make sense of this gradually. We're not done. Keep thinking here. So what happens if L is larger? How about L equals 2? Well, if L equals 2, now we're talking about a d orbital. And with a d orbital, we have the possibilities of m sub l are going to be from minus L to positive L with the integers in between. In that case, we end up with all of these values, minus 2, minus 1, 0, 1, and 2. That's a total of 5 values. And I didn't write it down, but for L equals 1, there are 3 values possible for m sub L. So let's keep going, see if we got the pattern now. And the next quantum number. So each of these magnetic quantum numbers reflects a different orientation of an orbital in space. If we wanted to take this one further, for L equals 3, that would be F orbitals. And we won't focus on those, but let's just continue the pattern for now. Then the values of m sub L would be from minus 3 to positive 3 and all the numbers in between. So what do you get? Minus 3, minus 2, minus 1, 0, 1, 2, 3. That's a set of how many possible values? It looks like 7 values. Now, we won't go that far very often, but the pattern will continue each successive value of L. So each of those are going to be important to us because the magnetic quantum number tells us the orientation of the orbital in space. Well, let's get some more information then. When we're looking at the p orbitals, there are 3 orientations in space. Either the 2 lobes of the p orbital lie on the x-axis, and it's called p sub x, or the lobes of the p orbitals, there are 2 of them, they are going to potentially land on the y-axis instead. When they're along the y-axis, we'll call it p sub y. And p sub z correspondingly then the 2 lobes of likely probability where the electrons occur are going to be oriented along the z-axis. So they're all perpendicular to one another. And notice that there's a 0 probability or very, very small probability of any electrons occurring at the actual the origin, at the intersection of all the axes. Now, when you get to d orbitals, they get very much more complex, and you are not responsible for remembering which ones have which names, but some aspects of this have some logic to you, but it's not tricky. They're not critical to be specific with this. The d orbitals are 5 different types. Now let me go back to my previous thought here. Remember that with the p orbitals, we had 3 values. So that means there's 3 different orientations for p orbitals in space. With the d orbitals, there were 5 values. And that means there are 5 orientations for d orbitals in space. So going to this diagram from your text, you see 3 orientations for the p orbitals, and you have 5 orientations for the d orbitals. Now, knowing the names and understanding the pictures of the p orbitals is one thing, but d, as again I said, are a little more complex. You'll notice that 4 out of 5 have 2, they look like twice as many lobes as a p orbital, and then the last one is something else different that's like a p orbital with an extra ring around the middle. That is beyond our concerns. You don't need to explain those or remember the labels that go with them. All right, so how do the magnetic quantum numbers correspond to each of these? When you have the first p orbital, that would be for m sub L is minus 1. When you have m sub L equals 0, that gives us the second one. And when m sub L is 1, that gives us a third orientation of a p orbital. So correspondingly, we'll have magnetic quantum numbers for the 5 d orbitals. They're going to go from minus 2 to positive 2 with the integers between. So here comes the magnetic quantum number as minus 2 gives us the first one. The magnetic quantum number of minus 1 gives us the second one. The magnetic quantum number of 0 gives us the next. And magnetic quantum number of 1 and magnetic quantum number of 2. So each of them corresponds to a unique combination of n, the principal quantum number, the letter L, the angular momentum, and the magnetic quantum number. All right. Wow, that's a lot to think about. The diagram that I tend to think will be the most helpful for all of us is to use this table from your textbook, and it shows the allowed or possible combinations of quantum numbers, N, L, and M sub L, for the first 4 shells. 4 shells gets us down to the row that begins with potassium. And so if you have N being the first shell, N equals 1 is the first shell. It's also the first row on the periodic table, and it correlates to that exactly, and that will be row number 1. And when that is 1, N is 1, L will be 0. There is no other choice because there's only one type of subshell. M sub L is also 0 because you can't go minus and plus 0 to get other values. And the notation for that shell is going to be 1s. The 1 tells us that this is the principal quantum number, and the S tells us the subshell type. The subshell derives from L equals 0. Every time L equals 0, it's going to be an S subshell. So the same thing correlates on the next row. N is going to be 2, and when L is 0, we have another S subshell, but it's in the second shell, and so it has a number in the front correlating to the second shell. Now, expanding then from L equals 0 to L equals 1 in this row, pardon me, I'll take that extra line out. When L equals 1, there's 3 possible values of the magnetic quantum number. Remember now that N tells us the shell, the L tells us the subshell, it describes a subshell, and then this is M sub L is going to tell us the orientation of the possible subshells. They're going to derive from M sub L. So when L equals 1, there's 3 possible orientations, and those are only first found in the second shell. We don't have L equals 1 until the second shell. And so at shell number 2, we have our first P subshell because L subshell is always going to give us a P. An L quantum number gives us the P subshell. So L equals 1 gives a P subshell. Now, the P subshell has 3 orbitals. Unlike the S subshell, it's got 3. They're going in 3 different directions. We looked at their diagrams. And so in the previous slide, and you'll get used to this more as we talk about them more. Again, when we go down to the third shell, we still have an S subshell, but this time it's 3s. It's going to have a larger radius than the previous 2, but it still corresponds to the value of L equals 0, and that gives us the S subshell. When it's in the third shell, that's what the 3 tells us. When you go to the third shell, continue the third shell, we again have the possibility of L equals 1 with 3 values of M sub L, and those are going to be the 3p, third shell, p electrons. P electrons always correspond to L equals 1. And there are 3, as we said in the previous shell, possible orbitals in any P subshell. P is the subshell. And then when we get to the third shell, we now have the possibility of one more value of the angular quantum number, L, and that's going to give us a value of 2. And whenever we have 2, L equals 2 is going to result in a D-type orbital, but there's 5 of them. They go from -2 to +2 in the M sub L values, which gives us 5 orbitals in that subshell. Again, this is in the third shell, and that's why the number is in the front is going to be 3. The previous row, again, 3p, that corresponds to its being in the third shell as well. So if you look at each shell, there are progressively more orbitals in each shell, and there are going to be more complex possibilities yet in the fourth shell. They correlate a lot, and the only piece that's new different now is that we now have the option of L equals 3, where there's going to be 7 possible orbitals in those F subshells. So L equals 3 corresponds to F subshells, and they only first occur when you are in the 4th shell, not any sooner. Now, these will take some practice. I will fully tell you that I have to practice these every time I return to the quantum numbers because they're not something we're going to use every day, but they help us explain electrons. Electrons are the whole quest here. So the bottom line is this. We're going to have energy levels that correlate to each of these shells and subshells. As I stated a little bit ago, the energy level of the first shell is always going to be the lowest. And so when you look at, whoops, trying to make my extra mark go away. When you look at this diagram for the hydrogen atom and the levels, energies of the orbitals within hydrogen, the first shell is the lowest energy. The second shell comes a little higher, the third shell higher, and correspondingly the fourth one is higher. Don't worry about the numbers there, but you can see you go from a low number to a larger number each time. When you look at a multi-electron atom, there is going to be some variation in the order of these subshells based on the fact that one electron will influence the energies of other electrons. And so there will be some splitting of the second shell into 2 different energy levels, the third shell into 3 different energy levels instead of just 1, and similar for the fourth shell. But guess what? The fourth shell now is going to overlap with the third shell, making that a little more interesting to describe. We'll get there gradually. Okay, that's enough to talk about quantum numbers for now. I will end this recording for this section and move on to another recording for the next part of the chapter.